Let's back up for a minute and look at this form of the equation we had from earlier. We're going to generalize a little bit. This term up here was just change in potential energy, and we made it a specific one to get to the Nernst equation. But now we're backing up and saying, wait, let's just put in change in potential energy. If we do that, we can think of this in context of the atmosphere and say the concentration of the atmosphere at some height y over the concentration at the ground level is e to the minus mgy over kBt. So here's our final expression for that. One caveat on this is this is at constant temperature. In a lot of these small systems we're dealing with, that will in fact be true. But when you think about the atmosphere, constant temperature by no means holds as you go up in the atmosphere. It gets colder and then it gets hotter and it gets colder and it gets hotter. All kinds of things happen. However, it does set the expectation that the concentration of air as you climb a mountain is going to go down, and it's going to go down exponentially. This is why humans live in a very thin amount of air around the planet. We cannot go very high. Um, we go up over about 2 miles or up over 10,000 feet or so, and we begin to struggle because there's simply not enough air for us. Another way to get to the same result, the way we would have done in a physics course before, is look at the pressure above and below a thin layer of air, and you get, using the ideal gas law, you get the derivative of the concentration with respect to height is minus mg over kBt times the concentration. This is a differential equation, the solution to which is this right here. So you get the same result from two different methodologies. If we look at kinetic energy in any one direction, what we get is the kinetic energy goes as kBt over 2 in one direction. Well, kinetic energy adds, and so if you want to know the total kinetic energy, you got to have the kinetic energy in all directions. And so we end up with the expected value or the average value of kinetic energy of a molecule is 3/2 kBt. The term on the left is just the average kinetic energy of the particles, so we can write this as the average kinetic energy is 3/2 kBt. The heat capacity is the amount of heat you put in for any given change of temperature. The heat capacity we often use, lowercase c, is a specific heat, right? Heat, because this has mass and everything in it, and this takes mass out. If we keep the volume constant, with the system can do work, and then the first law of thermodynamics reduces to change in energy equals Q, then we get to the heat capacity for constant volume. That's what this little CV means. Heat capacity for constant volume is partial U with respect to temperature with volume held constant. This is different from heat capacity at constant pressure. Right? So there's constant volume heat capacity, constant pressure heat capacity, two different things. One way to think of it is if you have a gas that you're adding heat to and you're letting it expand freely, that's constant pressure. If you have a gas that you're adding heat to and you're holding it the same volume, that's constant volume. Chemical potential. Um, let's look at this system and what the symbols on it mean. One, this system is isolated from everything else because they got the double wall on the outside. And here it's saying both energy and particles can be exchanged across the barrier there, right? So if we start off with, let's ignore this, they can only exchange heat. We know we get here, because we've been there before, which is equivalent to if they can only exchange heat, then the temperature on the two sides is going to be the same. All right. And in terms of entropy, the entropies on the two sides are going to have this relationship, but they can only exchange heat is not always going to hold true. So now let's look at what happens if they can exchange particles. So if a molecule can go from one side to the other, well, the total number of particles is a constant. And so we just have to think about what this means for where we are, right? The most probable state still satisfies this. We're now keeping U and V constant. in terms of entropy, we still have this, still have partial of the entropy with respect to the number of particles with U energy and volume constant equals the partial of entropy in the other side with respect to the normal number of particles. So the entropy changes with respect to the number of particles are equal on both sides. That's where we're looking at, we're in equilibrium, right? The most probable state is our equilibrium state. So if we go back, remember temperature is defined as this. So the equilibrium is again defined as T is equal to T prime. Similarly, the chemical potential is defined as, this is by definition, is minus T times the partial of S with respect to N. So let's back up. Partial S with respect to U. This is our entropy. This is in terms of the entropy. This condition is saying that the temperatures have to be same. Here we have a different quantity. We have N. We're defining T times that as our minus T times that as our chemical potential. And what does this mean? This means here we're told we're in equilibrium when the temperatures are equal. And here, pardon me, here we're in equilibrium when the chemical potentials are equal. So both thermal and diffusive equilibrium exist when temperatures are equal and chemical potentials are equal. And what about the system as a whole? If we look at delta S prime, it's the difference in the chemical potentials over the temperature times the change in the number of particles on side N. All right, so if a particle moves from a system of higher chemical potential to one of lower chemical potential, the entropy of the total system increases. All right, higher chemical potential to lower chemical potential, entropy increases. Okay, that's it for this bit of the lecture. There's probably just one more.